Hello students, welcome back to CLARIconcepts, Unleashing Conceptual Learning. Today in this lecture, we will be talking about the Pascal's law. This is the very basic law of fluid mechanics, and I request you to concentrate on this lecture. We are going to derive the Pascal's law and try to understand what is the concepts behind this Pascal's law. Okay. So let us say I have a container and I have a fluid filled in that, right? And the fluid is stationary. What did Pascal said is, Pascal said that at any given point, let's say suppose here, at any given point in a fluid which is at rest, the pressure that fluid will have from different directions, let us say here at this point pressure is P1, P2, P3 and P4, that a particular point has some different direction, fluid pressure, right? So Pascal said that at any given point in a fluid at rest, the pressure coming from or pressure acting from different directions will be equal. So P1 equals to P2 equals to P3 equals to P4, right? Similarly, you take another point somewhere over here. Again, let's say you have pressures from every direction. You mark any direction, right? So let us say pressure is P5, P6, P7, P8, whatever. So then P5 equals to P6 equals to P7 equals to P8. This is what Pascal has said. Where P5, P6, P7, P8 are the pressure from different directions but at a given point. Now see to this. Many a time students get confused in this particular topic that Pascal has, they will take it another way, that Pascal has said that pressure at all the different points in a fluid at rest is same. It is not like that. Pascal said at any given point, pressure from different direction will be equal. It doesn't mean that pressure at this point will be equal to pressure at this point. See, there is a difference. Again, I am repeating it. Listen it clearly. Pascal have never said that pressure at this point equals to pressure at this point. So pressure at two different points will be same. Pascal has never said that. Pascal said that pressure at a given point coming from different directions will be same. On a same point, pressure from different direction will be same in a fluid at rest. So now today what we will be doing? We are trying to derive or we are trying to prove this. We cannot directly believe what Pascal said, right? So we will prove that. So what Pascal said, first of all we will see the statement. Pascal's law is said that the intensity of pressure at a point in a fluid at rest is equal in all directions. You see this, you mark this point. Equal in all directions, meaning that at any given point, the intensity of fluid pressure from different directions will be equal. Clear? So let us prove this first. So for proving what we will take, I will take one simple point, and in this point, let's say I will mark a simple fluid element of wedge shape. You can see this wedge shape fluid element. Now here I will have pressures, let's say P1 from one side, P2 from another side, P3 from another direction. Let's say P1, P2 and P3. And I will try to see whether P1, P2, P3 are coming equal or not. So firstly, let me zoom into this picture, and this element has been zoomed. A single point has been zoomed and it is something like this, so that to give you more clarity. So what I will do, I will first of all draw various lines. So I will draw the axis. Let us suppose this is your x-axis, this is your y-axis and this is your z-axis. So the distance on the x-axis of this element, let us say this is delta x for example, which is very small. Again from here to here, this is let's say delta z, because it is in z direction, and the vertical height, let us say it is delta y. And let us suppose that this length, the slant length is somewhere some L meters for example, or L, just value L, and the angle between the horizontal and this is, let us say, theta. Let me draw you from some different color to give you more insights of this. This is a theta, right? Now as we discussed, pressure from three faces is different. Let me show you that pressure. I will mark some pointers. So let us say this particular corner is A, this is B, this is C, this is D, this is E and this is F for example. So pressure on the face A, B, C, D, which is somewhere over here, this particular face, the left face, the pressure experienced by this face is, let's say, P1, right? Pressure experienced by the bottom face is, let's say, P2, and pressure experienced by the slant face, so I'll just also mark this This is bottom face and this is the slant face, right? So pressure on this face is, let's say, P3. Now if at all in our derivation or conclusion, if this 3 pressure comes to be equal, P1 equal to P2 equal to P3, then I can say that whatever Pascal has said, it is true. If that doesn't come equal, I will not believe that, right? Now how will you make sure they come equal or not? We will simply use a mechanics principle. How? Pressure are responsible for transferring the force. This fluid is at rest. Now when fluid is at rest, I can say that it is in equilibrium condition. That means each of this element of the fluid is in equilibrium condition. When some element is in equilibrium condition, that means you take summation of forces along any direction. Let's say x, y or z. The net answer should be 0. If the net force is not 0, then there must be some acceleration with the fluid element. That means there should be some movement. But here the fluid is at rest. That means it is in equilibrium, and that means the net force in x direction and y direction and z direction should be equal to 0. Now we will see. Now for all the forces, first of all, to understand whether the net force is 0 or not, I need to make sure whether I have represented all the forces on the element or not. Now for any element, there are 2 types of forces. One is body force, another is surface force. Now if I talk about body forces, body force here will be the weight. So weight will act downward, right? W, weight will act downward. And surface force, basically it will be pressure forces. So force on face A, B, C, D will be towards right side, and I am representing it by the value F1, and the value of this force will be P1 times the area. What is the area? This is delta Z into delta Y. Delta Z into delta Y. Yes? Delta Y, sorry. I will just... So this F1 basically is pressure into delta Z into delta Y. Okay. Now then force on the bottom face A, D, F, E will be perpendicular to the surface always, and the value is F2, and this will be pressure at this face, that is P2 multiplied by this area. This area is delta X into delta Y. Delta X into delta Z, not Y. Right? And then the third force, which is F3, and the value of this will be pressure P3 into L times delta Z. This is the area, right? L delta Z. Okay. Now if I want to resolve these vectors into x and y direction firstly, right? So I will use summation of x equal to 0, summation of y equal to 0. But before that, I need to make sure that all the vectors are either along x or along y. So F1 is totally along x, okay, perfectly fine. F2 is totally along y, okay, it is fine. W is along y, it is fine. This is a vector which is at inclination, F3. So what we need to do is, we need to break this vector into 2 mutually perpendicular vectors, one component along x, one component along y. So how do you do that? Let me show it to you. Whenever you want to resolve this vector, what you do is, I want to resolve this into 2 mutually perpendicular directions in x and y. So I will draw a lines from the tail point and the head point of the vector parallel to x and y. Similarly, I will draw the line from the head of this vector parallel to x and y. Now you can easily see the one component of the vector will be this from tail to this point, and one component will be this. So this component is along y, this component is parallel to x-axis. Now question is, which is this angle theta? Now how do you make sure this? See, this line is perpendicular to this line. This line is perpendicular to this line. So if both of these has angle theta, then both of these should also be having angle theta. So if this is theta, what is this? This is F3. So this will be F3 cos theta, because angle is coming in between, and this will be F3 sin theta. So we will resolve these vectors into 2 mutually perpendicular components. So we will not use F3 as such, we will use both these components individually. Clear? Now what is W? Let me talk about W. W I'll just mark over here. W is the weight, which is mass into gravitational acceleration. What is mass of this object, this fluid element? That will be density times volume into G. What is volume of this fluid element? Volume is the area of this triangle and then multiply by the perpendicular length. So area is 1/2 delta x into delta y, and then delta z is the perpendicular length, right? So rho into 1/2 delta x delta y delta z into g. This is the weight. So we will use this also in the equation. So now we have got all the forces 1, 2, 3 and 4, right? Now what we will do, we will try to use the equation. So first I will use the equation called summation of forces along x to be equal to 0. So let me talk about what are the x forces. One is this, forces along x direction. One is this is in y, this is in y, this is in y, and another is this. There are only two components, right? One in positive x, one in negative x. So I will say F1 is positive minus F3 sin theta is negative equal to 0. You can check. F3 sin theta is in negative x direction, so I will put minus. F1 is along positive x, so you will put plus. So I will just denote this x and y, right? What is F1? F1 is P1 into delta z into delta y. P1 into delta z into delta y. You take this right hand side, you will get F3 sin theta. What is F3? F3 is P3L delta z. F3 is P3L delta z into sin theta. Okay. Now delta z will get cancelled from both the sides. You will remain with this P1 delta y to be equals to. Now what is L sin theta? You can check. What is L sin theta? If you look at this triangle, I will draw it over here. This is the triangle from front view. This is theta. This is distance L, this distance. This distance is delta x and this is delta y. So can you say from this triangle that delta x is equals to L cos theta and delta y is equals to L sin theta? Again one and the same. Or you can say sin theta equals to delta y by L. Sin theta equals to opposite by hypotenuse, delta y by L. One and the same. And cos theta equals to adjacent by hypotenuse, delta x divided by L. So now if you have L, just a minute, if you have L sin theta, what can you replace with that? You can replace delta y in place of L sin theta. Just do that. I will put P3 into delta y in place of L sin theta. So this will get cancelled. Ultimately, you will left with this P1 equals to P3. So you have got one conclusion, equation 1. What? That in this P1 equals to P3, meaning what? P1 equals to P3. So these two pressures are equal. Now we will talk about this P2. So now what we will do? We will try to do summation of forces along y to be equal to 0. For forces along y, you need to check the forces. See, F2 is positive because it is along positive y. W is negative. Also F3 cos theta is negative. So what you will do is, F2 is positive, W is negative, minus F3 cos theta is also negative, equals to 0. Now what is F2? F2 will be P2 into delta x delta z. Delta x delta z. You take both this term on the right hand side. This will be W plus F3 cos theta. So P2 delta x delta z should be equals to, what is W? W is 1/2 rho delta x delta y delta z and g. This is 1/2 rho delta x delta y delta z and g, plus F3 is P3 L delta z into cos theta. Now you take delta z common from right hand side, common and out, and cancel it with this. So this 3 will get cancelled. Yes. Now if you look at this term, this is P2 delta x equals to 1/2 rho delta x delta y g plus, what is L cos theta? What is L cos theta? It is delta x. So L cos theta is delta x, so I will put it P3 delta x. So again take delta x common from right hand side and cancel it with this. Yes, so what you left with is P2 equals to 1/2 rho delta y g plus P3. Now if you look at this expression, see, you remember this thing that I had a point, and at this point there are 3 pressures from different directions. Now when this is a point, this element is also a point. When the element is also a point, this is a zoomed view of that. That means this distance is delta x, delta z, delta y are very small. Very small, matlab infinitesimally small. It is very close to 0. Now that means delta y is close to 0. That means this can be neglected in comparison to P3 and P2. It is very negligible. So when you neglect this, delta y is 0, so this term will go to 0, and therefore P2 will be equals to P3. And that means equation number 2. So you compare equation 1 and 2. If P1 equals to P3, P2 equals to P3, that means what? Ultimately I can say that P1 equals to P2 equals to P3, and therefore Pascal's law is proven or proved. Right? So I hope you understood this. So now what you can say with this? P1 equal to P2 equal to P3. Now you see, in P3 I have not given any value of angle. The reason for me to take this triangular or wedge shape element, because the theta, that means P1 equals to P2 equal to P3 is valid for all the value of theta. That means if you take theta equals to 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, and as and when you change the theta, the angle of P3 will also keep on changing. And therefore, you can say that pressure from all directions will be equal at a given point. Clear? So I hope you understood this. We'll meet you soon in the next class where we will learn another concepts on fluid mechanics. Log into our website clariconcepts.com to get more information on such conceptual videos. Thank you so much.